Imagine a world where doctors can detect skin cancer with the precision of a detective and the speed of a supercomputer. But here's the challenge. Traditional methods struggle with irregular lesions or take too long to process. That's where SegDT steps in, a revolutionary model reshaping medical image segmentation. Let's dive into how it works, why it matters, and why it's a game changer for healthcare. Medical image segmentation is the art of isolating specific regions in a scan, like pinpointing a skin lesion. For years, convolutional neural networks, CNNs, like UNet dominated this space. They excel at learning local patterns, but they're blind to long-range dependencies, like solving a jigsaw puzzle without seeing the full picture. Then came transformers, inspired by language models, which use self-attention to grasp context across an image. But they're computationally heavy, like a supercomputer running on a smartphone. Enter diffusion models, which iteratively refine images from noise. Think of it as painting by numbers. While highly accurate, they're slow and resource-intensive, making them impractical for real-time use. So how does SegDT bridge this gap? It's a diffusion transformer, a hybrid of CNNs, transformers, and diffusion models, optimized for speed and efficiency. Let's break down its architecture. SegDT starts with a VAE encoder, which compresses images into a lower-dimensional latent space, making processing faster. Then a patch embedder divides the image into tiles, like puzzle pieces, for localized analysis. The core is its DI-T blocks, 12 specialized layers that use self-attention to detect global patterns and cross-attention to incorporate contextual clues, like lesion texture or shape. It's a team of experts collaborating to refine the final output. But here's the innovation. SegDT skips the traditional image reconstruction step. Instead, it trains directly in the latent space, cutting training time dramatically. During inference, it starts with noise and uses rectified flow to accelerate the diffusion process, like skipping ahead in a recipe to reach the final dish faster. This reduces steps from 35 to 15, slashing processing time by nearly half without sacrificing accuracy. The results? SegDT outperforms state-of-the-art models on datasets like ISIC 2016, 2017, and 2018, achieving near-perfect dice coefficients, a measure of segmentation overlap, and high specificity, identifying healthy tissue. It uses 10x fewer parameters and 15x less computational power than competitors, making it viable for low-cost hardware. This means hospitals with limited resources can access cutting-edge diagnostics, democratizing advanced care. But SegDT isn't just fast, it's adaptable. Researchers are already refining it to handle tricky cases, like tiny or irregular lesions, by integrating patient data. The open-source code invites global collaboration, turning this model into a foundation for future breakthroughs. In a world where every second counts, SegDT isn't just a technical marvel, it's a lifeline. By merging efficiency with precision, it's paving the way for smarter, faster healthcare. As AI evolves, models like this will transform diagnostics, making early detection accessible to all. Stay curious, and let's keep pushing the boundaries of what's possible.